All right, so welcome to lecture 11, the method of least squares. This is one of my favorite topics to do. I was originally planning on doing something else, but I got an email from someone in the class late last night, or maybe it was yesterday. It's taking me a while to get through a lot of my emails, talking about trying to do a regression to predict how COVID might be spreading in some communities based on various pieces of data. And I thought this was an outstanding question, and I thought it was worth to change what I was going to do today and talk about how to do regression. And what I'm going to try to do is have the lecture function for those who have seen regression before, so that there will be some advanced material. We may not get to all of that in this lecture. Some of that might have to come to the next lecture. And then your assignment will be to do regression to some extent. It will be an extremely open-ended assignment so that you can determine what you want to do. The more parameters you have, if you know linear algebra, it's not really that troublesome. It's trying to find what are the most important parameters. If you are selling a house, what do you think matters most in selling a house? Location. And in fact, real estate, they often say location, location, and the third item, location. What else might matter?
Square footage.
I figure out what the price should be. So what else would go into figuring out what the price of a house should be? One is location, yes? How renovated is it? Now, again, if it's a really old house, that could be valuable. It's a classic. It's a colonial house. It has history. We looked at one of those when we were buying a house in the Boston area, but we kind of, at some point, didn't want to be walking in strange convoluted manners to get through some of the small passes. What else? Size, number of rooms, types of rooms, number of bedrooms. Lot size, do you have a large lot? Do you have a place where kids can play in the back, where you can have fun? So there's a lot of different things. And you need to try to figure out how much is each one worth. The more factors you put in, hopefully the better estimate you will have. At the end of the day, though, how much is a house worth? As much as someone is willing to pay. How much is a ball player worth? As much as someone is willing to pay. So if you have a couple of people who overpay, if you try to do an analysis like that, that can greatly affect your outcome. And we're going to talk about different ways of measuring errors. There are some errors that are more important than others. Sometimes you want to make sure that if you err on one side rather than the other. I assume everybody has been in an elevator at some point in their life. I might have already given this example. What is the first thing I look at when I enter an elevator? The weight capacity. And then you quickly check around and say, yeah, it should be pretty safe today to ride this elevator. You want to make sure that you stay well below the true weight capacity. Almost surely, if it says 2,000 pounds, it can do more than 2,000 pounds. You always have a little bit of a safety margin. When they build bridges, another great example of something like that. All right, so introduction. So here is simulated data for a spring test. What is your first thought when you see this? Nothing is labeled, right? Thou shalt label. Right? There are so many things where I can manipulate how things look by changing the labeling, by changing the scaling. Have I shown this XKCD before? Okay, I thought I showed this one before. And so just, labeling is important. So the force in newtons is the y-axis, and the displacement in meters is the x-axis. And I basically just simulated data with, Gaussian errors. So it should look linear. That as you displace it more, the force increases by a constant proportion, and that proportionality is the spring constant. I believe when Hooke first published this law, he published it as a Latin anagram. Thankfully, we do not do this anymore for scientific discoveries, but this was a way to basically, I think, tell the community, I've got the result to establish priority without necessarily giving it out. All right, so the best fit line, and we'll talk about that in a little bit, is 4.99x plus 0.48. And this gives us A equals about 5 and B is about 1/2. And my theoretical line was y equals 5x. So if you look at this, if I go over about 20 units in x, I go up about 100 units in y. So the change in y over the change in x, 100 over 20, that looks like 5. So it looks like it should have a slope of 5. Having a best fit line giving me a value of 4.99x, that's pretty good. The 0.48x, though, that's off a little bit from 0. Which do you think is the more important number, the slope A or the intercept B? Yes, the slope. Why is the slope more important? It determines the change. So as x gets larger and larger and larger, the impact from the intercept becomes less and less and less. And I really want to know how things are changing. It's the slope that's going to matter. Okay, and so we're going to talk about the method of least squares. It's one of my favorite methods in all of mathematics and statistics. Amazingly, the most cited work I have in my entire academic history is some lecture notes on this that I wrote when I was a postdoc at Brown. And every now and then I get an email, your most cited paper was, really? But it's a wonderful, wonderful method. There is another way, instead of using the method of least squares, what do you think least squares involves? Squares, right. You can use the method of absolute values. And when you use the method of absolute values, you get a best fit value of A of 5.03 and a best fit value of B that is less than 10 to the negative 10 in absolute value. Looking at that and looking at where the data is coming from, I would say that the absolute value method is doing a better job than least squares. And we'll talk a little bit about why this might be true, but why we might still like to do least squares. All right. So here are 3 different choices of how we could do the error analysis. So say we observe yi, that's our output, and xi is the input. And we believe there's a linear relationship. So we believe y equals ax plus b. Again, this is all written up in great detail in some notes that I will give you after the lecture. So we believe y equals ax plus b. And so here's 3 ways of looking at the error. I can look at observed minus predicted. I can look at the absolute value of observed minus predicted, or I can look at the square of the observed minus the predicted. Any Monty Python fans here? Or is this one of these is right out? Which one is a bad choice of error? The first one. Why is the first one bad? I'm sorry? Okay, so what's wrong with the negative error? Yeah, you can actually have a negative error canceling a positive error. Imagine you have 2 data points. One is at the bottom left and one is at the top right. What is the best fit line going through those 2 data points? Bottom left, top right. Yeah, okay. Yeah. So what line would I draw? Bottom left, top right. Those are my 2 data points. What's the best fit line between them? Yeah, draw the effing line, right? You've got 2 points determine a line, just draw the damn line. But if I took the top left and the bottom right and drew the line connecting them, the errors would cancel and it would have as good of a fit. You do not want an absurdity like that. Now we come down to E2 versus E3, absolute values and squares. And I know some of you have seen this lecture before, so you have lost your voice. Can anybody give me a reason to choose either 2 over 3 or 3 over 2? And you can defend both. Both are defensible.
3 seems that it might be easier to algebraic and manipulate.
Good. So squaring is a much easier operation than absolute value. In particular, what kind of function is the square function versus the absolute function? And you need to have seen at least Math 130 or 140 to answer this.
Differentiable.
Differentiable, excellent. So thank you, Zoomland. So the absolute value function is not differentiable. When you look at what's going on near the origin, you have a v. If you move a little bit to the right, it looks like the slope is +1. If you move a little bit to the left, the slope is -1. The squaring function is differentiable, which means all of the tools of calculus are available. Several of you have 3 calculus classes in the bank by now. Wouldn't it be nice to use them? So that's why we like 3 over 2. The problem with 3 is if you have one bad data point, it can completely screw things up, because you magnify errors by squaring them. So if you have one point that's off, it is going to greatly pull the entire best fit line. When I was an undergraduate at Yale, I had to participate in psychology experiments for a psych class I took. And we were told for one of the things it was going to be between 5 and 15 minutes. And the experiment just kept going on and on and on, 30, 35, 40 minutes. And then I noticed, oh, it looks like there's a camera on me. I wonder if this is an experiment on frustration, because I was getting very frustrated. And I started to have some fun with the questions that they were asking. So they were giving us objects moving left to right, and you had to guess their speed relative to the speed of the initial object. And sometimes they would spin, sometimes they would be large, sometimes they would be small. I started answering things like purple or dinosaur. And then I decided to give, I think, 60 digits accuracy for my speed, and it just overflowed the system, and the system crashed. And I said, excuse me, TA, it's no longer working. Now, they assured me that it was not a frustration experiment. It was a coincidence that that light was on. And they don't understand why, because the questions are supposed to be random. It shouldn't have taken more than 15 minutes. I shouldn't have been in there for 40 minutes. Do you think my data point should be included? No. And so a lot of times you can make a case that this data point should be thrown away, that this should be removed, that it's a bad observation. But in the squaring, one bad observation, an error of 2 magnifies to 4, which is a lot worse than 2 errors of 1. I like to phrase it as, if I am the consultant, I like to use the squaring. If I am hiring the consultant, I would like them to use the absolute value. The absolute value forces you to do numerical approaches. The squaring has a closed form solution. Right. So if you have not seen calculus, do not worry. I'm going to just try to sketch a little bit of what's going on. If you've seen multivariable calculus, we basically take the partial derivatives and set them equal to 0, and we do some algebra, and we come up with the solutions for A and B. And I will expand this out a little bit more. For those of you who are in 119, all that you need to know is that there is a procedure that gives us the best fit values for A and B. And what this means over here, this means the sum n goes from 1 to n of 1. So we just add 1 n times. So 1 plus 1 plus 1, that's just going to be capital N. This means we sum n goes from 1 to big N of xn times yn. So we would just multiply x1 times y1, add to that x2 plus y2, add to that x3 plus y3, and so on. It's a nice, clean, explicit formula. There's no simulations that need to be done. There is no, well, in my best opinion, this is what I think we should, there's no decisions. It's entirely forced on us. It's like the quadratic formula. You plug in the inputs, you plug in A, B, and C, and out come the answers. All right, so just to give you a little bit of a sense of the theory as to where this comes from, here is my error function. And the error, which is a little bit confusing, is actually a function of the variables A and B. X and Y are not variables. X and Y are the known data. There's only one situation that we have to be careful to avoid. Imagine you believe that the time it takes a ball to roll down an inclined plane depends on the angle. So you think that as you change the angle, it should change how long it takes the ball to roll. You're going to go to the lab and do the experiment. Tell me what data you would like to collect. You believe the time depends on the angle. Tell me what data to collect. Okay, so tell me explicitly. Treat me like a moron. Tell me what to do. Good. So you're giving me measure it at several different angles. What if I always measure it at 45 degrees and I want to try to figure out how the time depends on the angle if I don't change the angle? Should I have any hope in hell of seeing a relationship? That's the one thing you have to avoid. If you want to determine how y varies with x, you better have x vary. And as long as you do that, the method of least squares will work. The only way it will break down is if you don't do that. So we want to find the values of A and B that minimize the error. And it should make sense that there is going to be a minimum. If you send the slope a off to positive infinity or negative infinity, the error should explode. Same thing for sending b to positive or negative infinity. So there should be a minimum value. And this is where we use calculus. So if you have a function of one variable, if the first derivative is positive, that means if you increase x by a little bit, you increase. If you decrease x by a little bit, you decrease. So you can't be at a maximum or minimum if the first derivative is positive. Similarly, you can't be at a maximum or minimum if the first derivative is negative. So the only possibility is if the first derivative vanishes. That doesn't mean you have a maximum or minimum. We have functions like x cubed, which does not have a maximum or minimum at 0, where the first derivative vanishes. But generally, these are the candidate points. These are the points to look at. And so if we have a function of two variables, just do it twice. Make sure you're at a point where if I take the derivative with respect to a, and that just means keep b constant, imagine b is fixed, nail it down, and then just vary a. And then nail down a and vary b. And we want both of those derivatives to be 0. And now, as was remarked, now we just do the algebra. So when we take the derivative with respect to a, we get 2, then our quantity to the first power, and then the derivative of the inside with respect to a, and that's going to be negative xm. And then we take the derivative with respect to b, and when we take the derivative, it's going to be negative 1. And now we just have 2 unknowns. We can divide by negative 2, it's just a constant. This is just algebra now. The algebra is done in full detail in the notes. You do not want to see it done in full detail here, so I will just refer you to the notes if you want to see it. All that matters if you're taking this as 119 is the ability to use regression. This is one of the more powerful tools we have in statistics. And so we can rewrite the equations. So on the previous page, I have the sum of yn times xn. I'll just bring that over to the other side as the sum of x and yn. Over here I have, I'm sorry, I'll keep it on this side. I have the sum of negative a xn xn. That's the sum of negative a xn squared. Because it's negative, I move it to the other side. And because a is a constant, a does not depend on n. It's not indexed. It's only the x's and the y's that are changing. So I can pull a outside of the sum. Now I'll just get this sum times a plus this sum times b. Is that sum? This is just a number. It's just summing the squares of the x's. If I knew what they were, I would just do that right now. So even though it looks complicated, it's just a number. I have some multiple a plus some multiple b is another multiple of a plus another multiple of b is something else. So 2 equations, 2 unknowns. You can write it in matrix form if you're comfortable with matrix form. Your matrix acting on AB equals blah. And then if you remember your matrices, I can take the inverse of a 2 by 2 matrix, and we can use that to find the solution. And so we would just take the inverse of the matrix. The matrix is invertible as long as its determinant is not 0. And it's a nice fact that you can write the determinant of the matrix as basically something that is essentially the sample variance. Morally, it's like the sample variance. X bar is the average value of the x's. So this is just an algebraic statement. But notice that as long as the x's vary, as long as they're not all the same, as long as they're not all x bar, the determinant will be non-zero and the matrix will be invertible. So this is just a little bit of advanced math to show that the process works. When you do it in practice, it will always work. This is why, so long as you let the x's vary. And so we get the following explicit formulas for a and b. There's lots of different ways of writing them depending on which quantities you want to isolate. It really doesn't matter. This is something that can be done trivially in Microsoft Excel. You don't need advanced programs for this, though of course there are some available. We could also, as I said, write it like this. This is another equivalent way of writing things. One of the things that I always like to mention is your answer reasonable? So you want to think about what units do things have. So if y equals ax plus b, let's say x is in meters and y is in seconds. Well, if y is in seconds, what are the units of b? If y is in seconds, what are the units of b? Seconds. If x is in meters, what are the units of a? It's got to be seconds per meter. And so you can then go through and see, well, if I put in x is in meters and y is in seconds, this will give me meters second. And this will be meters squared down here, meters second, meters squared down here. Yes, it's going to come out as A is going to have units of seconds per meter. And it's really nice when you can do a quick dimensional analysis check like this to see that your answer is reasonable. All right, and as I said, there's other ways of doing the algebra. So another way of doing the algebra is putting in things, say I had 4 equals 3 plus 3a plus 2b, 5 is 2a plus 5b. We can solve for b in terms of a, substitute, solve for a, and once we have a, we can then solve for b. So again, we don't need the advanced linear algebra. That's going to become more useful if you want to have something depending on 3 items. So right now we can only do ax plus b. It would be nice if we could do maybe ax squared plus bx plus c. Or maybe we have more parameters to go through. So right now, if you're going to try to apply this to a COVID model, you get one input. And you make your prediction based on that. Do you think this is a good idea? One number.
No.
No. And I will risk doing this as an aside. So this is the draft of the letter. Actually, it has been sent to the Commission of Education as well as other people. This is from the work I did with the metrics group, just arguing that what we are doing right now for the state color coding is not optimal. And we are basically just choosing colors based on just one number. The average case per day per 100,000. It's simple, it's easy to use, but it's missing a lot of information. And so I talk about some of the proposals, and the one in particular that I have sent them was basically, well, the simple version is to just take the case rate per 100,000 and multiply by the minimum of 7 divided by R and 1. And so we'll assume each town tests at least at the 7% level. And if you test more than that, if you test twice as much at the 14%, you would multiply by 714, so you would have your test count. If you tested 21%, you would have 1/3 of the effective rate. There will be no penalty if you test fewer than 7%. So you're not going to magnify your test, your case count. Yes? So I chose 7% to just a little bit overestimate what most towns were doing. Most towns were doing 5%, so that you don't start getting any credit until you're already above the average of what people are doing. So it's a good question. I wanted to just give a little bit of leeway. You could actually make things a little bit better and actually have not just 7 over R, but 7 over R to the dth power to decrease how much of an effect this has. And so over here, if D equals 1, it's cutting down a lot. If D equals 1/2, it doesn't cut down as much. So there's a lot you can do in terms of trying to come up with a reasonable formula. The idea, as we talked about last time, is if you're only testing a subset of the population, you don't have complete information. And so you somehow want to take the case rate and magnify that to get a true sense of what's going on. But this is only using one piece of data. And so those of you who are doing this class as 315, you will be doing regression where you will have more than one piece of information. For those of you who are doing it as 119, you only have to use one piece of information. Okay. Do you think you will do better or worse if you have more information? Do you think the model should do better the more information you include? Hopefully it will be more accurate. And as long as things are linear, we should be able to do stuff like this. Now, what's important is it doesn't have to be linear in the variable you're considering. It just has to be linear in terms of how it comes in. And so I'll talk more about that very soon. All right, so regression extensions. So we did y equals ax plus b. Most things in life are not linear. And so if we could only apply this to straight lines, we're in trouble. The first extension is, well, what if I had y as a1 f1 of x plus a2 f2 of x and so on and so on? So I have k functions. Maybe the first one is going to just be x, the second one might be cosine of x, the third one might be exponential of x. I have some kind of mix like this. And as long as the mixing, as long as the weighting is linear, a1, a2, a3, the same argument will apply. And all that will change is rather than having the sum of xi, you might have the sum of f1x, f2x2, so, something like that. It's going to just change things a little bit. So most relations are not linear, but they can often be linearized. Everyone by now has assumed, I will assume, has seen the logarithm function. And there's a bunch of nice log laws. When you saw logarithms in class, did your teachers ever tell you why we care? Was anybody ever given an explanation of why we care about the logarithm? So this is a crime, right? You can bring this to the attention of the American Mathematical Society. We will send a representative to your school district. You should not be here without knowing why we care so much about logarithms. More importantly, we don't want the next generation to be put into the same situation. Logs are wonderful. One of the best log rules is the log of a product is the sum of the logs. We have a lot more experience with summing. I would much rather sum than multiply. This is in fact how slide rules are. I changed to a new backpack because my old backpack has sadly had too many years of climbing things around campus. One of my aunts, well, technically first cousin once removed, she's a physicist, I'm a mathematician. Everybody else in our family became an engineer. So we've always had a special bond. She married an engineer, of course. And he had a slide rule tie clip. And I will try to remember to bring that into the next class. Out of curiosity, how many people know what a slide rule is? Okay. How many people know what a tie clip is? So before calculators, people used slide rules to do calculations very quickly. And the whole point is if you take logarithms, you convert multiplication to addition, and then you invert and you get back to the original number. So let's say we have Newton's law of gravity. F is some universal constant times the product of the masses divided by the square of the distance between them. Let's assume we believe that mass, the mass is going to be fixed for the problem, the gravitational constant is fixed for the problem, and we believe force is proportional to some power of the radius. So we'll write F equals BR to the A. If we take logarithms, the log of F, and then we have the log of BR to the A. The log of a product is the sum of the logs. So we get the log of big B plus the log of R to the A. The log of R to the A is A log R. And so I'm just letting little b equal the log of big B. So we now see that there's a linear relationship between the log of big F and the log of R. And so those will be my new variables. So now the role of X will be played by log of R, the role of Y will be played by log of F. Here are 25 of the most populous cities from several years ago. I grabbed them somewhere from the web. And again, you've got to be very careful as to what is the definition of a city. Are you doing cities, metropolitan regions? And here's a plot of the rank of the city. Is it the most populous, second most populous, et cetera, versus the population? Can anybody look at this and tell me the form of this, or the best fit curve that goes through this? I can't. But if I plot the rank versus the log of the population, I still can't. But if I plot the log of the rank versus the log of the population, it actually kind of looks like a line. And so here's 100 of the most populous cities, and plotting the log, you can see it's actually pretty well given by a straight line. The point is a lot of relationships that are initially nonlinear become linear under this log change. This is looking at word counts. And again, I forget, this is again, bad slides. I forget where I drew this information from. Primarily because I don't really care. Do you think all sources of literature will give you the same word frequencies as to which words are most popular? So methinks you are right. So where might you get a difference in frequencies?
I guess what an astronaut looks like reading an article or a novel in an academic paper.
Right, so an academic paper versus a novel could be very different. What else could give you something very different?
Like Shakespeare and modern.
Right, Shakespeare and say a Schwarzenegger movie. You might have, although he did do a movie where he does have a Shakespeare scene, The Last Action Hero, but for the most part, I think you will see very different choices of words in a Schwarzenegger movie as you would see in Shakespeare. And so the sources will change a little bit, but again, if you do a log-log plot, you see that it's not that bad. It's not perfect, but it's not that bad in terms of a linear relationship. So a lot of times when you have your data, you should look at just the data straight out, take the log of one of them and not the other, and take the log of both. There's only 4 things to look at. That's a small enough number that you can do this. And you can often sniff out relationships that you would miss otherwise. So when you're looking at your regression, you might want to look at not just the regular data that you collect, but maybe logs of data. Right. So now, some examples. So the first one is actually an opportunity to join me on a publication. This is a project that should have been done years ago. So one of the hats I wear, as you know, is I serve on a regional school committee. I'm going to be very careful how I phrase this. For decades, the 2 towns, Williamstown and Lanesboro, have shared a middle high school, but the elementary schools were different. So the elementary schools were each a school district. The middle high school was a school district. How many school committees do you think we have? How many committees do you think we have for the 3 schools? When they were separate? Yes? 3. Actually, it was 4. Yes, that is how bad the administrative structure was. We actually had 4 committees. The 2 elementary schools had a super committee above them composed of subsets of them, which then formed an alliance with the middle high school committee and had it was an incredibly complicated administrative structure. We've been sharing resources for quite a while, and there was talk about maybe we should fully regionalize. And this is going to be very similar to the baseball paper or the baseball talk that I gave you. Keep it simple. What's a good model to do? Unfortunately, the state does not always have incentives to do things that might be best. So we had already had a lot of savings by we were sharing a superintendent and we were sharing other district personnel. If we were to fully regionalize and have 1 school district for the 3 of them, we would save an additional $120,000. How do you think we should assign that money between Williamstown and Lanesboro? And to just give you some information, not too much, Williamstown, say, has twice the population, and maybe Williamstown is a little bit wealthier. How would you split the $120,000 between the 2 towns? So maybe 60-40. Who gets the 60? So the small town, because maybe they don't have as much resources. You could also make the argument maybe the larger town gets it because they have more kids. Maybe 50-50, that's just a simple, fair way to do things. Can somebody give me a lower bound for how much money Williamstown should get of the 120? 0. And an upper bound? 120. So it should be somewhere between 0 and 120,000. If we regionalize and we use these state formulas, Williamstown would get negative $360,000 and Lanesboro would get $480,000. You can't make up these numbers. And I'm looking at this in horror. And I wanted to make sure that we never had a public vote at the school committee level while this was still being worked out, because I could not support having Williamstown pay $360,000 more. In previous years, I had actually worked with some people in Lanesboro when we were building the new middle school, high school. I thought the formula we had to allocate the capital cost between the 2 towns was unfair, and Lanesboro I thought was paying too much money. And I helped come up with a better formula that actually had Williamstown paying a little bit more than they would have otherwise, because the formula just wasn't fair. And when it came time for something like this, having a relationship like that was very useful, when I could say, look, it doesn't seem right that if the district is saving $120,000, Williamstown is paying $360,000 more. The problem was there's something called Chapter 70 funds. We have about 3.5 million coming a year to the district. When we were 3 different school districts, each school was given Chapter 70 funds, and we knew how much each school was getting. If we became a district, we only were told how much money goes to the district, and we had to allocate it. And the state was keeping their formula secret. But what information did I have? I had the data from the years before. What do you think would be worth doing? So if I have the data from previous years, what might I try to do?
Reverse engineer it.
Reverse engineer. So what method of mathematics or statistics should I use? Regression. This is a lecture on regression, right? This is probably an optimal example of regression. So our budget is around 21 million for the 3 schools. 3.5 billion is not insignificant. The state has a formula with lots of variables that was kept secret. So I wanted a formula that was fair, that did a good job predicting, that was transparent, and that I could explain. So again, this is very similar to what we're trying to do with the metrics. You know, keep thinking of my father who had the professor with 46 variables. Good luck selling that. It may be more accurate, but it might not also be something that people can understand or that you can even get the values for. And so I basically just used very little information. I used what was the population of kids in the 2 towns, you're going to each building, and what was the assessment of the towns, basically the sum of the property values, as a nice proxy for the wealth of the towns. And so what properties do we want the solution to have? We want the solution to exist. We want the value it assigns to each school to be between 0 and 1. We want it to add up to 100%. We want the values to be stable under small changes. So, you know, if your one more student moves into Williamstown, it should not greatly change how much money goes to Williamstown Elementary. That is exactly the problem we have right now with the metrics. It is not stable under one more observation. And as I said, we want the percentages to add up to 1. So turns out it can be done. This is the data for, I think, 2018. And so I made my predictions before the state came out because we hadn't regionalized then. And I was off by less than $10,000 essentially per building. Is $10,000 a lot? If anybody flat out says right now $10,000 is not a lot, please see me after class. In fact, see me after class every day from now on. Is $10,000 a lot? Why, yes. But that's not what I'm asking. I'm saying, is $10,000 a lot? Listen to the question. Yes. So imagine your Bill Gates comes in here. Does $10,000 really matter that much to him? Would he notice the change? Absolutely not. So it's always 10,000 relative to what? 10,000 out of 3.5 million, that's not a huge amount. That's essentially within the noise level. Okay, so as I said, many relationships are linear after you apply logarithms. So if y equals bx to the a, and when we take logs, we get log of y equals a log x plus b. So here's one of my favorite. Kepler has 3 laws of planetary motion. The first is you move in an ellipse with the sun on one of the foci, not bad. If you draw a line from the planet to the sun, it sweeps out equal areas in equal times, not so bad. And then the last is the Sesame Street law. One of these is not like the other. One of these just doesn't belong. If t is the orbital period of a planet traveling in an elliptical orbit about the sun and no other objects exist, then t squared is proportional to the length cubed, where L is the length of the semi-major axis. This one is a lot more involved than others. So the question is, imagine we didn't know Kepler's laws. And Kepler's laws was a key component in Newton's success in coming up with the theory of universal gravity. And Kepler could not have done this without terrific observations by Tycho Brahe and others. Could we discover this through statistics? Well, we could take the square root of both sides. You might as well have t to the first power. And you say t equals some constant to the L to the 1.5. And in fact, you should have known I was going to do this because I had a constant called b tilde. You normally don't introduce a constant with a tilde on it. So could we discover this through statistics? So here, sadly, is a list of the planets. It is different from the list of the planets when I was a child. What's missing? Pluto has been downgraded. I have a friend who knows the person who actually had to press the button on the official website to do the official downgrading. And I can talk about this when the lecture is not being recorded. So here is the data. I'm giving you the semi-major axis of the planets, and I'm giving them to you in astronomical units, where one astronomical unit is about 1.496 times 10⁸ kilometers, and I'm giving you the orbital periods in years. When you look at this, can you figure out where that constant b should be by looking at this data? T equals b L to the b times L to the a. When you look at this, do you have any idea what b should be? And if you look at the data carefully, it screams what b should be. Any planets you particularly like? Earth, good choice. Let's highlight Earth in red. Any thoughts now on what b should be? It should be 1. This is why I'm using astronomical units. I'm essentially choosing things so that the period of Earth is 1 and the length of Earth is 1, so that will force b to be 1. So we've talked about units before. So we've talked about smoot, and just because people may be watching this lecture who haven't heard the other lecture, I will do the smoot story again. Some of my other favorite units are the Bruno, the millihelen. The slug is actually really used. Anybody know what the Bruno is? It is the indentation in cubic centimeters formed by dropping a grand piano off the 3rd floor of a building at MIT. It's another one of these MIT units. All right. Here is one of the most compelling plots I've ever seen in my life. This is taking the orbits and the length of the semi-major axis of the 8 planets, doing a log-log plot, and looking how great of a job it does. It is phenomenal how well this does. This is the power of regression. We could actually use this to sniff out that maybe there is this law that maybe period squared is proportional to length cubed. And then I may give another lecture later in the semester on using statistics to sniff out relationships. Again, it's going to be much harder for what's going on with COVID because this is a really complicated model in terms of how things go on. There's a lot going on here. All right, so I have to do this just for completeness. Eventually you notice that certain professors like certain slides and you will keep seeing them. There are certain authors who have published many books and you will see the same images in book after book after book. This is the Harvard Bridge. The fraternity decided to see how many times it would take them to pick up little smoot and move them all the way down. I love that the fact that the uncertainty is 2 within an ear. And as I've remarked before, he ends up as the chairman of the American National Standards Institute. And the lesson is just don't miss an opportunity to seize an opportunity. You know, this is a funny, compelling story. When you are interviewing for jobs, you need to find a way to make a personal connection to a lot of them. For some things, it doesn't matter. We are looking for the best code monkey, and you have great code monkey skills. Great. But for a lot of other things, you need to make connections. Right now, for the metrics group, I am trying desperately to get people at the state to listen to this. You know, how do you write the letter? And before I sent it, time was short, but I sent it to a couple of people that I knew would respond very quickly with advice. And one of the pieces of advice was, you know, the first paragraph has to be much stronger in terms of what you want people to do. You're absolutely correct, yes. Put a bullet point on that. How do you want to sign it? As many of my titles as I can put down there to make me look as distinguished as possible. I'm not going to do the birthday problem. I will go back to the school district and say that, you know, if anybody is interested, I think this would be a great paper to write up as to how do you apply mathematics in a real world setting. And so now the regional agreement between Williamstown and Lanesboro has a regression that is done every year to say how we will be allocating the money coming from Chapter 70 funds between the two towns. And again, what I've been trying to argue all semester, you don't have to have the best result. You don't have to be perfect. You just have to be better than what is being done. It has to be an improvement. One of the dangers is what happens if we move significantly from where we are. Do you trust the formula to hold? Have I given you the quote from my high school textbook on special relativity? So it's amazing which things stick with you years and years later. And when I was a kid, I watched the TV show Super Friends. And I still remember the episode when Superman goes, "Great Scott, I promised to meet Wonder Woman at 7 in 5 minutes," and he flies off. And you know he's not going to leave her waiting. I don't remember why he needed to meet her on Saturn, but you were just convinced he was going to get there in 5 minutes. Later, when I learned about the speed of light, I was a little bit less convinced about that. My physics textbook in high school talked about the following special relativity results. And it said, now these results may seem counterintuitive, but you have to remember that most people don't have experience traveling at 3/4 the speed of light. I like the use of the word most. I'm still waiting to find somebody who has experience traveling at 3/4 the speed of light. One of the greatest dangers in life is to take an experience and extrapolate it beyond where you should. Mark Twain has a wonderful version of this. He has many wonderful sayings. It's essentially a cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one. To each experience in life, take only the lesson from it that you should. And so when we're trying to use these formulas, and again, when you do special relativity in honor of Einstein, you always do things with trains because that's the fast stuff from the early 1900s. If you have a train going west at 100 miles an hour, and you're on that train running west at 5 miles an hour, how fast do you look to somebody on the ground? So train's going 100 miles an hour, you're on the train running in the same direction the train is moving at 5 miles an hour. How fast does it look like to somebody on the ground that you're moving? About 105. Classically, Newtonian mechanics, the answer was 105 miles. That speed is additive. That your 100 from the train and your 5 from yourself get added together and you get 105. That's not quite right. There is a small correction factor. It involves basically the product of the speeds divided by the square of the speed of light. Another way of looking at it is it's the product of the fractions of the speed of light. Anybody know roughly how fast light travels? 3 times 10 to the 8 meters per second. Is that a lot? 186,000 miles a second. When you look at that, and you look at speeds of 5 miles, 100 miles, the ratio to the speed of light is essentially 0. I don't know if mankind has created anything that's traveling faster than, say, 50,000 miles an hour. I don't know if any of our probes have broken speeds even of that level. We have such a focused result of data that it is unreasonable to extrapolate it to speeds close to the speed of light, because we have no data there. Imagine you want to figure out how things depend on the angle, and you're going to measure things between 0 and 1 degree. You're going to have all your measurements between 0 and 1 degree, and then you're going to use that to extrapolate up to 90 degrees. You might be a little hesitant to do something like that. So, one of the issues is what happens for the formulas that we're using for the school committee if there are significant changes in the populations. How much of a change do you need before the formula gives you something that maybe does not make sense? So there's a lot of really good issues. So if anybody is interested, it would be nice to actually write this up and talk about what are the challenges in actually implementing something like this. So for your homework, and I will write up in greater detail, I want you to do something involving linear regression with something involving COVID. And I'll write it down more formally, but it's not going to be more explicit than that. You have complete freedom. Come up with a question related to COVID and come up with some data. Now, if you are only using linear regression with one free variable, you do not have that much opportunity. And so that might influence what you are trying to look at. And it is perfectly fine if you don't get a great relationship at the end of the day. I will also give you links to how you can have more than one variable. What if we have, this is like houses where we have location, we have size, we have number of bedrooms, we have lot. And the hope is that if you have more information like that, you will have a better predictive model. It is worth talking a little bit about how to gather data. If you use all of your data to train your model, how do you tell how good it is? You have to wait for more data to come in. And if it's not terrible to wait for more data to come in, that's not a problem. One of the things that I often do in baseball, a lot of people do stuff like this, is you break time into the even years and the odd years. And you hope that there's really no difference between the even years and the odd years. Is that a reasonable assumption? Most of the time. Do you think this year is like other years in baseball? No, they only have a 60-game season. So if you had told me last year that the Red Sox would lose fewer than 50 games this season, I would have been ecstatic. Now that I know that the season was only 60 games, much less so. When you look at number of home runs hit, number of wins, those numbers are not going to be comparable to other years. When you look at batting average or slugging percentage, those numbers might be comparable. Because you have a smaller data size, you might actually have more fluctuation. So it might be a really interesting experiment to see, is there more fluctuation in batting averages this year than in other years, because we haven't had the same level of averaging. So, again, when you're trying to do some stuff with COVID, you might actually want to say, maybe I'll break up the US into a bunch of different blocks. And I'll look at some blocks and try to use that to predict what's going to happen in others, and hope that they're going to be comparable. Or I'll break things up by weeks. You've got to be very careful. A lot of analysis, at Christmas time and that season is very different than the summer, is very different than March in terms of hiring, in terms of what's going on, in terms of shopping. So be very careful, think about all these things. All right, have a great rest of the day.